Humanity likes to believe in a simple story, that we began ignorant and primitive, slowly climbed out of darkness, and arrived, inevitably, at modern science. This story is comforting. It flatters the present, but it may not be true. Across the ancient world, there are signs that knowledge does not move forward in a straight line. Instead, it rises, concentrates, fractures, disappears, and sometimes reemerges centuries or millennia later. Civilizations collapse. Libraries burn. Skilled practitioners die without passing on their understanding. What remains are stones, symbols, and traditions stripped of their original context. The deeper archaeologists dig, the more unsettling the picture becomes. Structures older than recorded history show levels of precision that appear incompatible with the tools officially assigned to them. Astronomical alignment suggests long-term observations spanning thousands of years. Mathematical constants appear embedded in monuments built before formal mathematics was supposedly invented. This raises an uncomfortable question. What if ancient people knew more than we think? And what if much of that knowledge was lost? Modern science assumes progress is cumulative, but history does not support this assumption. The fall of the Western Roman Empire alone erased centuries of engineering expertise. Concrete recipes vanished. Road-building techniques were forgotten. Literacy collapsed across Europe. Knowledge that had once been common became rare, then mythical, and Rome was not unique. Long before Rome, the Bronze Age world experienced a sudden, near-total collapse. Around 1200 BCE, advanced civilizations across the eastern Mediterranean fell almost simultaneously. Writing systems disappeared. Trade networks collapsed. Cities were abandoned. Entire technologies vanished from use for hundreds of years. If such losses could happen in relatively recent history, how much easier would it have been for knowledge to vanish in deep antiquity, long before paper, printing, or digital storage? Prehistory itself may be misleading. The word suggests ignorance. Yet recent discoveries challenge this assumption. Hunter-gatherer societies once believed incapable of large-scale planning have now been shown to construct monumental architecture. Göbekli Tepe in modern Turkey dates to over 11,000 years ago, older than agriculture, older than pottery, older than metal tools. And yet it features massive stone pillars arranged with symbolic and astronomical precision. According to traditional models, such construction should have been impossible. If people could organize labor, quarry stone, transport multi-ton blocks, and encode symbolic meaning before farming even existed, what else might they have known? Mainstream explanations often rely on underestimation. Ancient people, we are told, were simply very clever with simple tools. But this answer, repeated often enough, becomes a shield against deeper inquiry. Consider this. Intelligence is not new. The human brain has not significantly changed in at least 200,000 years. What has changed is continuity, our ability to preserve and transmit knowledge across generations. Without stable institutions, knowledge is fragile. Ancient societies relied heavily on oral transmission. Skills were passed from master to apprentice. When a civilization collapsed, that chain was broken. Techniques that took centuries to refine could disappear within a single generation. Writing helped, but writing itself was rare, elite, and vulnerable. Clay tablets shattered. Papyrus rotted. Libraries were destroyed by war, neglect, or religious zeal. The most famous loss of all was the Library of Alexandria, but it was not unique. Countless collections vanished without record. What survived did so by chance. Even when texts remain, interpretation is a problem. Ancient language is symbolic. Technical instructions may be encoded as myth, ritual, or allegory. Without cultural context, meaning evaporates. This is why ancient knowledge often appears fragmented. We find the results, but not the method. The monument, but not the manual. The illusion of linear progress blinds us to this reality. We assume ancient people were experimenting their way upward toward us. But what if they were inheriting knowledge from even earlier cultures? Many ancient civilizations themselves spoke of golden ages, times when gods or ancestors possessed greater wisdom. Egyptian texts refer to Zep Tepi, the first time when divine knowledge structured the world. Greek philosophers believed earlier civilizations were destroyed by floods and fires, resetting humanity. Plato described lost advanced societies in his dialogues, insisting that Greek civilization was merely a shadow of what came before. He warned that repeated cataclysms erase human achievements again and again. Modern geology now confirms that Earth has experienced massive climate disruptions, floods, and impacts throughout human history. Sea levels rose dramatically at the end of the last ice age, drowning coastlines where early civilizations may have flourished. If advanced knowledge existed before these events, it may now lie underwater, physically and historically. The idea of lost knowledge is uncomfortable because it challenges modern arrogance. It suggests we are not the peak of human achievement, but one chapter in a longer, more fragile story. In the parts that follow, we will examine evidence that ancient civilizations possess sophisticated understanding of mathematics, astronomy, engineering, medicine, and natural forces, knowledge that sometimes rivaled and occasionally surpassed what emerged thousands of years later. Not to claim ancient people were magical or supernatural, but to recognize that intelligence, when given time and necessity, can reach remarkable heights, and that once lost, knowledge does not announce its absence. It leaves silence. If ancient civilizations were truly primitive, their structure should reflect it. Rough work, crude measurements, trial and error frozen in stone. Instead, what we find across the ancient world is precision so extreme that even modern engineers struggle to explain how it was achieved. The most famous example rises from the Giza Plateau. The Great Pyramid is often described as a tomb, but this word does little justice to the object itself. It is not simply a pile of stone stacked upward. It is a mathematical statement made physical. Its base is aligned to true north with an accuracy of less than 1/10 of a degree, more precise than many modern buildings constructed with laser-guided instruments. The four sides are almost perfectly equal in length. The structure incorporates the mathematical constant pi into its dimensions. The ratio of its height to its perimeter reflects relationships that would not be formally defined until thousands of years later. These are not coincidences easily dismissed. To achieve such alignment, builders would have needed advanced surveying methods. They would have required long-term astronomical observation, precise measurement tools, and standardized units of length. Yet according to conventional history, Egypt lacked advanced mathematics, precision instruments, and even a wheel at the time the pyramid was built. Something does not add up. Egyptian engineers moved stones weighing up to 80 tons with remarkable accuracy, placing them so tightly together that a razor blade cannot fit between joints. Even today, replicating such masonry without modern machinery is extraordinarily difficult. Official explanations often invoke vast labor forces and simple tools used over long periods of time. But effort alone does not produce precision. 10,000 workers with poor measurements will still produce a crooked result. Precision requires knowledge, and Egypt was not alone. In Peru, the ancient builders of Sacsayhuaman carved massive polygonal stones, some weighing over 100 tons, fitting them together in complex interlocking patterns. The stones are cut with such accuracy that they resist earthquakes, shifting slightly and then settling back into place. There is no mortar, no gaps, no room for error. The stones are not uniform blocks. Each one is uniquely shaped, sculpted to match its neighbors in 3 dimensions. This implies advanced planning, modeling, and stoneworking techniques that remain poorly understood. What tools were used to carve granite and diorite, stones harder than iron, into such precise forms? Copper tools, as often suggested, would have been inadequate. Even with abrasives, the level of control displayed is astonishing. Across the world, similar mysteries appear. At Baalbek, in modern Lebanon, ancient builders quarried and moved stones weighing over 800 tons, some of the largest stones ever cut by human hands. They were placed with remarkable precision, forming foundations that later Roman engineers chose to build upon rather than replace. The Romans themselves, masters of engineering, seemed impressed by what they found. In India, ancient temples incorporate mathematical ratios that align with astronomical cycles. In Cambodia, Angkor would encode solar and lunar measurements into its architecture, functioning as both a temple and a calendar. These structures suggest a unified understanding of geometry, astronomy, and engineering. Geometry, in particular, appears deeply embedded in ancient design. Sacred geometry, often dismissed as symbolic, may have been a practical language for transmitting mathematical knowledge before formal notation existed. Circles, squares, triangles, and proportions appear again and again. These shapes are not arbitrary. They are fundamental to measuring space. Ancient builders may have used geometric constructions rather than numerical calculations, allowing them to achieve precision without written equations. This would explain how advanced mathematics could exist without surviving textbooks. Measurement systems themselves hint at lost sophistication. The ancient Egyptian cubit was not a rough estimate based on a human arm, as often claimed. It was standardized to a degree that implies institutional control and calibration. Cubits were carved into stone rods, preserved as reference standards. These rods ensure consistency across massive building projects spanning decades. Such standardization is a hallmark of advanced engineering cultures. Beyond architecture, ancient civilizations demonstrate a remarkable understanding of land measurement and geodesy. The placement of major Egyptian sites appears to reflect geographic relationships across the Nile Valley. Some researchers argue that the Giza complex mirrors celestial patterns, while others note alignments between monuments separated by great distances. Even if some interpretations remain debated, the underlying fact remains. Ancient builders were measuring large-scale space with confidence. In South America, the Nazca lines stretch across kilometers of desert, forming geometric patterns visible only from the air. Creating them required planning on a massive scale, careful surveying, and precise execution. These are not random scratches. They are controlled designs laid out across uneven terrain. How were straight lines maintained over such distances without aerial perspective? How were proportions preserved? Again, knowledge is implied. Engineering knowledge also appears in ancient infrastructure. Long before modern plumbing, civilizations constructed complex water management systems. The Indus Valley Civilization featured standardized brick sizes, covered drainage, and sophisticated urban planning over 4,000 years ago. Streets were laid out in grids. Wastewater systems ran beneath homes. Such organization suggests centralized planning and technical expertise. In ancient Rome, concrete allowed for domes, aqueducts, and harbors. Yet the precise recipe for Roman concrete, especially its ability to harden underwater, was lost after the empire collapsed. Modern scientists only recently rediscovered why Roman concrete was so durable. This is a recurring theme. Knowledge achieved, knowledge forgotten, then slowly rediscovered, often centuries later. Perhaps the most striking example of ancient mechanical understanding is the Antikythera mechanism. Recovered from a shipwreck off the coast of Greece, this device dates to around 100 BCE. At first glance, it appeared to be a corroded lump of bronze. But X-ray imaging revealed something astonishing inside, a complex system of interlocking gears. The mechanism could predict eclipses, track planetary cycles, and model astronomical motions with remarkable accuracy. It is often described as the world's first analog computer. Nothing like it appears again for over 1,000 years. Its existence suggests that ancient Greek scientists possessed mechanical and mathematical knowledge far beyond what survived in texts. And this device was not unique. It was likely part of a broader tradition of scientific instrument making that vanished with political collapse and cultural shift. When societies fall, specialists disappear, workshops close, techniques die with their practitioners. Written records alone cannot preserve applied knowledge. Engineering is not just theory. It is practice. Once practice stops, knowledge decays rapidly. The monuments that remain are survivors, not representatives. They show what was possible, not what was common. And they force us to confront a difficult possibility, that ancient civilizations were not stumbling toward knowledge, but managing, refining, and sometimes losing it. Long before telescopes, satellites, or digital clocks, ancient civilizations were already watching the sky with obsessive attention. They tracked the movement of the sun, the moon, and the wandering planets. They recorded eclipses. They mapped stars. They built monuments that aligned not just with seasons, but with cosmic cycles lasting tens of thousands of years. This was not casual stargazing. It was systematic, mathematical, and deeply embedded in culture. Across continents and millennia, Ancient peoples oriented their most sacred structures toward the heavens. Temples, pyramids, stone circles, and cities themselves were aligned to solstices, equinoxes, and key stellar events. At Stonehenge, massive stones framed the rising sun at the summer solstice and the setting sun at the winter solstice. The site functions as a solar calendar carved into the landscape. Its construction required long-term observation, precise geometry, and generational knowledge transfer. Stonehenge is older than writing in Britain, yet its builders understood solar cycles with extraordinary clarity. In Egypt, temples were aligned so that sunlight penetrated inner sanctuaries on specific days of the year, often marking royal anniversaries or cosmic events. Abu Simbel, carved directly into rock, allows the sun to illuminate statues deep inside the temple on only 2 days annually. Such alignments cannot be accidental. They demand calculation. They demand prediction. Prediction requires data collected over time. Time, for ancient astronomers, was not merely counted. It was understood as cyclical. Many ancient calendars extend far beyond a single human lifespan. The Maya long count calendar, for example, tracks time across thousands of years with astonishing precision. It is capable of recording dates millions of years into the past and future. This was not because the Maya believed the world would end, but because they conceived of time on a cosmic scale. Their calendar system combined solar, lunar, and ritual cycles into an interlocking structure of mathematical elegance. It required sophisticated arithmetic, including the use of zero, a concept that would not appear in Europe until much later. The Maya tracked the cycles of Venus with such accuracy that their predictions differ from modern astronomical values by only minutes. Venus, associated with warfare and power, was observed obsessively. Its appearances and disappearances were recorded over centuries, revealing a deep understanding of synodic periods. This level of precision implies continuous observation over many generations, and continuity is the key. Astronomy is not learned in a lifetime. It is inherited. In Mesopotamia, Babylonian astronomers recorded planetary motions on clay tablets for centuries. These records allowed them to predict eclipses with remarkable accuracy. They recognized repeating cycles, such as the Saros cycle, which governs eclipses every 18 years. These discoveries were not accidents. They were the result of patient data collection and pattern recognition. In China, astronomical records stretch back thousands of years. Chinese court astronomers documented comets, supernovae, and planetary conjunctions with precision that modern astronomers still rely upon. One of the most famous examples is the supernova of 1054 CE, recorded by Chinese observers and now visible as the Crab Nebula. Such records demonstrate that ancient observers were capable of objective, systematic science. But perhaps the most mysterious astronomical knowledge relates to precession, the slow wobble of Earth's axis that causes the position of stars to shift over a cycle of approximately 26,000 years. This cycle is subtle. Detecting it requires comparing stellar positions across many centuries. And yet, there are indications that ancient civilizations were aware of it. Plato hinted at long cosmic cycles that reset civilization. Ancient Hindu texts describe vast ages of time, yugas, that span hundreds of thousands of years. Egyptian iconography features recurrent motifs linked to stellar rebirth. Some ancient monuments appear aligned not to the stars of their own era, but to those of a much earlier time. The Great Sphinx of Giza, for example, has been argued to face the rising constellation of Leo as it appeared around 10,500 BC, an alignment consistent with the Epic of the Lion. While controversial, such interpretations raise important questions. How could ancient builders encode stellar positions from epochs thousands of years removed from their own? One possibility is mythic memory. Another is inherited astronomical tradition. Or perhaps civilizations existed earlier than officially recognized, observing the sky long before the dawn of recorded history. Timekeeping itself reveals lost sophistication. Ancient sundials were calibrated with precision. Water clocks measured hours at night. Star clocks use a rising of specific stars to mark time. These systems required standardized units and careful calibration. They also required an understanding of latitude, since stellar risings differ by location. This suggests ancient astronomers were not only observing the sky, but mapping Earth, Celestial and terrestrial knowledge were linked. In many cultures, the heavens were mirrored on the ground. Cities were laid out as cosmic diagrams. Sacred geography reflected celestial order. This integration of astronomy and architecture suggests a worldview in which science, religion, and governance were inseparable. Astronomers were not fringe observers. They were central figures. Their knowledge regulated agriculture, ritual, navigation, and power. Navigation itself depended on the stars. Long before compasses, sailors crossed oceans using stellar navigation. Polynesian navigators memorized star paths, wave patterns, and wind behavior, enabling them to traverse thousands of kilometers of open ocean without instruments. This knowledge was oral, embodied, and precise. When colonial contact disrupted these traditions, much of this navigational science nearly vanished. Another example of how knowledge can disappear without written record. Astronomy also intersected with cosmology. Ancient cultures understood the sky as dynamic, not fixed. They tracked changes, cycles, and anomalies. Comets were recorded. Eclipses feared but predicted. Planets recognized as distinct from stars. The word planet itself comes from the Greek for wanderer. Recognizing wandering bodies among fixed stars requires careful, repeated observation. It requires patience. It requires memory. And it requires a scientific mindset. The assumption that ancient astronomy was merely mythological is increasingly untenable. Myth may have been a language, but observation was the foundation. When myths speak of gods moving to the heavens, they may encode planetary motions. When stories describe ages and destructions, they may reflect astronomical cycles tied to climate change. In this way, ancient sky science may be hidden in plain sight, encoded, symbolic, but real. In the next part, we will descend from the sky back to Earth, into the body, the material world, and the hidden sciences of medicine, metallurgy, energy, and forgotten technologies that suggest ancient knowledge extended far beyond what we typically imagine. When we imagine ancient technology, we often picture stone tools and simple remedies. Yet the historical record tells a far more complex story, one in which ancient civilizations probed the human body, transformed raw materials into advanced alloys, and experimented with natural forces in ways that modern science is only beginning to reappraise. Ancient medicine was not merely superstition layered over guesswork. In many cases, it was observational, procedural, and surprisingly effective. In Egypt, medical papyri revealed detailed anatomical knowledge. The Edwin Smith Papyrus, dating to around 1600 BCE but likely copied from far older sources, describes surgical procedures, trauma treatment, and diagnostic methods based on observation rather than magic. Wounds are examined. Prognoses are given. Treatments are categorized as curable, contestable, or untreatable. This is clinical thinking. Egyptian physicians understood the importance of cleanliness. They used honey as an antibacterial dressing, copper salts to prevent infection, and moldy bread, an early form of antibiotic, on wounds. They practiced dentistry, set fractures, and performed surgeries that required anatomical familiarity. This knowledge did not emerge from ritual alone. It emerged from practice. In India, ancient Ayurvedic texts outline surgical techniques, including cataract surgery, cesarean sections, and reconstructive procedures. The physicians Sushruta describe hundreds of surgical instruments and detailed methods for anesthesia using herbal compounds. Some of these techniques would not appear in European medicine until the modern era. In the ancient Andes, skulls bearing evidence of trepanation, surgical drilling, show signs of healing, suggesting high survival rates. These procedures required precision, understanding of cranial anatomy, and infection control. Ancient healers were experimenting. They were observing cause and effect. They were refining methods over generations. Medicine, however, was inseparable from material science. The substances used in treatments reveal advanced chemical knowledge. Resins, minerals, plant extracts, and metals were processed deliberately to produce specific effects. Metallurgy, in particular, stands as one of the clearest indicators of lost technical sophistication. Across the ancient world, metals were not simply melted and shaped. They were engineered. The Hittites mastered ironworking centuries before iron became widespread. Their techniques were closely guarded state secrets. When their civilization collapsed, iron production spread. But the original mastery was diluted. In India, wood steel was produced using methods that created carbon nanotube-like structures, resulting in blades of legendary strength and flexibility. These techniques vanished for centuries. Roman concrete, capable of self-healing and enduring seawater, was forgotten after the fall of Rome. Modern science only recently rediscovered the role of volcanic ash and lime clasts in its durability. Such losses are not trivial. They demonstrate that technical recipes can vanish even when physical examples remain. Materials science also intersects with acoustics and resonance. Ancient structures around the world appear designed not only to be seen, but to be heard. In Mesoamerica, step pyramids produce chirping echoes that mimic the call of sacred birds. At Chavín de Huántar in Peru, underground galleries amplify sound in disorienting ways, likely used during ritual initiations. In ancient theaters, such as those in Greece, acoustics are so precise that a whisper on stage can be heard clearly from the highest seats. This is not accidental. It suggests deliberate study of sound behavior. Sound is energy, and energy appears repeatedly in ancient technological experimentation. One of the most controversial artifacts in this category is the so-called Baghdad battery, a clay jar containing a copper cylinder and iron rod, dated to the Parthian period. When filled with acidic liquid, it produces a small electrical current. Was it battery? Mainstream explanations vary, but the object demonstrates that ancient people could generate electricity intentionally, or at least stumbled upon the principles. Electricity is not magic. It is a natural phenomenon. Ancient observers encountered it through static shocks, lightning, and electric fish. Greek texts describe electric eels used to treat pain. Roman physicians prescribed them for headaches and gout. This implies awareness of bioelectric effects. Magnetism, too, was known. Lodestones were used in navigation in ancient China long before the compass became widespread. Energy knowledge did not require equations. It required observation. Heat, pressure, vibration, and flow were studied through experience. Consider ancient water systems. The Persians built qanats, underground aqueducts that transported water across deserts using gravity alone. Some still function today. In Sri Lanka, ancient engineers created massive reservoirs and canals with precise gradients, maintaining water flow across vast distances. These systems required surveying, hydrology, and long-term maintenance planning. In the Roman world, aqueducts delivered millions of liters of water daily, using carefully calculated slopes. Too steep and erosion would occur. Too shallow and flow would stop. Balance was essential. Balance implies knowledge. Ancient technologies also extended into optics. Lenses made of rock crystal have been found in Assyrian contexts. While their exact purpose remains debated, their craftsmanship suggests experimentation with magnification. The Lycurgus cup, a Roman artifact, changes color depending on light direction due to embedded nanoparticles, an effect modern nanotechnology seeks to replicate. The Romans did not know the word nanotechnology, but they understood results. Results matter more than theory. Perhaps the most overlooked aspect of ancient science is its integration. Modern disciplines are separated: medicine, physics, engineering, chemistry. Ancient knowledge was unified. A healer understood plants, minerals, and the body. An architect understood geometry, astronomy, and acoustics. A priest might be an astronomer, engineer, and physician combined. When such integrated systems collapse, recovery is difficult. Fragments survive, but coherence is lost. This may explain why ancient knowledge appears incomplete. We have pieces, but not the whole. And when later civilizations inherited these fragments, they often misunderstood them. Ritual replaced technique. Symbol replaced function. What once worked became myth. This does not mean ancient civilizations were more advanced than today in every respect. It means they were advanced in different ways. Ways shaped by environment, necessity, and continuity. And continuity, once broken, is hard to restore. In the final part, we will examine how knowledge disappears on a civilizational scale, through collapse, catastrophe, and cultural amnesia, and ask what lessons modern society must learn if it hopes to avoid repeating the same cycle. Knowledge does not vanish all at once. It erodes. It fractures. It disappears quietly, often without anyone noticing until it's already gone. Civilizations fall for many reasons: climate shifts, resource depletion, war, disease, internal decay. But when they fall, something more fragile than buildings collapses with them: continuity. Without continuity, knowledge cannot survive. History provides repeated examples. The fall of the Western Roman Empire did not destroy science overnight. It disrupted institutions that preserved it. Roads fell into disrepair. Aqueducts crumbled. Skilled engineers disappeared. Literacy declined sharply. Within a few generations, concrete recipes were forgotten. Surveying techniques vanished. What had once been routine engineering became miraculous legend. And Rome was relatively recent. When we look deeper into antiquity, the losses grow larger and quieter. The Bronze Age collapse around 1200 BC erased entire civilizations across the eastern Mediterranean. Writing systems like linear B disappeared. International trade networks collapsed. Cities were abandoned. For centuries afterward, societies regressed technologically. Ironically, it is in these gaps that myths are born. Stories of gods, heroes, and lost golden ages often appear after collapse, not before. They may be cultural memories of a world that once functioned better than the one that followed. Ancient texts themselves warn of this cycle. Plato described repeated destructions of civilization by floods and fires, leaving only scattered survivors who have forgotten nearly everything. He insisted that advanced societies existed long before his own time, and that their knowledge was erased by catastrophe. In India, Hindu cosmology speaks of vast cycles of creation and destruction, with humanity rising and falling across immense spans of time. Knowledge is lost, then slowly rebuilt. In Mesoamerica, destruction myths describe previous worlds ending violently, each age leaving behind fragments. These stories may not be literal histories, but they may encode a deeper truth. Earth is not stable. Modern geology confirms that dramatic climate shifts occurred at the end of the last ice age. Sea levels rose more than 100 meters, drowning coastlines worldwide. If early advanced societies lived near coasts, as most do, their remains now lie underwater, submerged, unseen, unstudied. Archaeology is biased toward what survives. Stone survives. Metal sometimes survives. Wood, textiles, and paper do not. Neither does applied knowledge without teachers. The greatest symbol of lost knowledge is the Library of Alexandria. More than a building, it was an institution, an attempt to collect all human knowledge in one place. Its destruction, whether gradual or sudden, represents something far more devastating than burned scrolls. It represents broken transmission. We do not know what was lost there. We only know it mattered. And Alexandria was not unique. Libraries existed across the ancient world, in Mesopotamia, India, China, the Islamic Golden Age. Some were destroyed by invasion, others by religious reform, others simply by neglect. When political power shifts, knowledge often becomes expendable. New regimes rewrite priorities. Old sciences become heresies. Practitioners are silenced. What survives is often what aligns with authority, not what is most useful. Even when texts endure, context fades. Technical instructions without skilled practitioners become riddles. Symbols without shared meaning become art. Ritual replaces function, and eventually, even ritual is forgotten. This is why ancient knowledge appears fragmentary. We find the outcome, but not the process. The monument, but not the method. The artifact, but not the training that made it possible. Modern science, for all its power, is not immune to this fragility. It depends on infrastructure, specialization, and global stability. Disrupt those, and knowledge becomes vulnerable. Digital storage feels permanent. It is not. Without electricity, without maintenance, without continuity, modern data becomes unreadable faster than stone erodes. We are not as secure as we think. Ironically, modern science is now rediscovering principles that ancient civilizations seem to grasp intuitively. Holistic medicine is returning. Sustainable architecture echoes ancient design. Passive cooling, acoustic engineering, and natural materials outperform modern shortcuts. Even astronomy is revisiting long-term cycles once dismissed as myth. The past is speaking again, not loudly, but persistently. This does not mean ancient civilizations were superior. It means they were different. They optimized for longevity, balance, and continuity within their environment. We optimize for speed. Speed forgets. The greatest lesson ancient civilizations leave us is not about lost machines or secret technologies. It is about humility. Knowledge is not guaranteed. Progress is not permanent. And intelligence alone is not enough. Without preservation, wisdom collapses. Perhaps the most dangerous assumption of modern humanity is that we are the final version. History suggests otherwise. Civilizations rise. They master their world. They grow confident. Then they fracture, and what follows remembers them only through fragments. Stone, story, silence. The ruins we study today were once the peak of human achievement. One day, our cities may be studied the same way. The question is not whether ancient civilizations had lost scientific knowledge. The evidence suggests they did. The real question is whether we will lose ours, or whether we will learn, at last, that knowledge must be protected as carefully as it is pursued, because once it is gone, it does not announce its absence. It simply leaves silence. If this journey through lost knowledge has revealed anything, it is that humanity's greatest achievements are not carved in stone, but carried in memory. If you believe the past still has something to teach us, take a moment to reflect, preserve curiosity, question assumptions, and remember that the line between civilization and forgetting is thinner than it appears. If you want more deep explorations into ancient history, lost science, and humanity's forgotten chapters, support this work. Subscribe, share, and keep watching, because the past is not finished with us yet.